one benchmark system for what has it?
Well, kind of both. I've coded my own simulation in C, and it's basically just an array with all the... I'm actually getting to that, but I can take it now. I don't have an actual network. Instead, I have an array with structs, with one struct for each node with the data that node knows about. So that's actually the nodes. So for instance, 4,000 nodes. And then I have code a loop that simply walks through them and does the operation for each node. Connection, sharing data and everything. And I let this loop run. And then I kind of ask it questions by asking it to put in some values and gather some statistics and print that, so I can see. I get a print call, like print for every round. I print a result and I see how these values change. For instance, if I'm testing net split prevention, I have my network. It just runs the network, and then I insert a value and broadcast it through the nodes. Then I wait some rounds and see if the message, all nodes get this new number. If they don't, then we have a net split. Then I know it just reached 50% of the network, then I know we have a net split. So that's how I test for net split. So it's very simple. So it's just some pages of code. So just an array with structs and run this loop. So the problem is, that's why it takes me 2 weeks to come up with the simulation, because I always have to think, what do I want to test? How will I ask it? Should I insert stuff to see what happens? And then usually take 1 day debugging to make it work. So first it can be crashed, and then I realized that it might be a bug, and I had to debug it, and it just works. And I've been very lucky. Most things have just worked. It's like, I thought, for instance, my first net split prevention algorithm, had lots of fixes and tricks to prevent it. But I thought it was too much to simulate, so I simplified it. It's just the simple great thing that should crash once an hour. But it never crashed. And now I run it for 100, what would be 100 years of real world time, and it still hasn't crashed. So actually I have to make it even worse and see it crash, and then calibrate my mathematics. Now I think it crashes once every 400,000 years. But I'm not sure, because I'm missing. So that's how I do my simulations. I might probably talk a bit more about it. We have other problems like flooding, overloading. There's several kinds of overloading that happens in peer-to-peer networks, so most people are not aware of them. There's ways. One of them, for instance, is if you have kind of a random network, if you have a primitive algorithm to connect to nodes, new nodes just connect to 5 other nodes, then old new nodes that are very visible, that have been in the network for a long time, tends to be more visible people, and they will get more connections. They are, in graph theory, I think they are called a hub. Gets richer, they get more and more connection. And I say that's a very, very bad thing, because that node will end up with 10,000 connections, and that's a bad thing, of course, and lots of traffic. But the theorists, they think that's good, because when they discover that in nature and almost any algorithm you come up with have this problem. It was actually slightly hard to find a way to not get this effect. But then back in the 60s or something, when they started this, they realized that they thought that, well, these nodes help. That means the network has shorter distances. So the hubs are good, they're really good. And we get them anyways, we say they're good. But for me as a old network guy, I say, no. So almost all of the networks we have out there, like the BitTorrent DHT, the algorithm seems to create hubs a lot, I think. And that's bad. So some nodes are actually working harder, and other nodes are helping out. So I'll show you how to avoid that later on. But what we can do some things we can do to prevent overloading is we can have round-based algorithms that whatever we do, we just send message once a minute. So we have a rhythm that will work with. For instance, when we broadcast things, we just don't keep broadcasting them immediately, because most things we broadcast don't have to be broadcast immediately. We can package everything together and send the whole block once a minute. That means we don't send too much. That also means, as you know, in IP packets, there's a header. There's a, what do you call that extra stuff in English? Overhead. Sorry. Header and overhead. That's overhead. So sending data, it has an overhead. But if you package together to, say, 200 bytes of several small messages, there's just overhead once. So you save a lot of overhead by sending or rocks like that. The other thing you can do is throttling. Throttling is a bit evil, but you have to do it. For instance, if you get stuff from all your neighbors, you're supposed to send it further on, you refuse to send too much. You have a limit. I don't never send more than 50 messages a minute to my neighbor. So if I have more to send, I start throwing away messages. Internet router does that, and that's the only way to solve some problems. You just refuse to flood your neighbor. So that's throttling. And we'll look at throttling a lot, because throttling isn't necessarily bad, it's a good thing if you do it the right way. The next thing we can do is use randomized algorithms, which is my area, because I use all my stuff is randomized. That means, well, peer-to-peer network is chaotic, as someone mentioned. Nodes go on and offline, different nodes do different tasks and stuff like that. But if you increase the randomness, by the nodes, when they do work, they can use an internal digital dice to decide what to do and when to do stuff like that. You can actually spread the load evenly. So with more randomness, you can reach good randomness. You can get it smooth and even, and then on top of that, you can create order. And we'll look at a lot more. I'll explain that when I show the elements. That's actually not something I realized earlier. That was a result of when I figured out things that weren't. I suddenly realized that's what I'm doing all the time. So you can't really think that let's search for the randomness and then use that. Actually, that would be a result, but we can understand why they throttle things that way.
Are there any situations in this where the quality of randomness matters? Or
yes.
So you have to have good quality.
For instance, if your say the number generator is too bad, you can actually crash the network.
Okay.
You can net splits because you have too bad randomness in your algorithm choosing which nodes you will connect to.
Okay.
So yeah. So but good random number generators, we have lots of them. That's no problem. You can use any one of the good ones. It doesn't matter. It doesn't have to be perfect. It have to be good enough. So actually,
it doesn't repeat too often.
Yeah.
Zero random would be fine.
Yeah, two
It's
numbers
not very small.
Yeah. So even that, so the worst ones, the default ones in C are too bad. But any one from any operating system is more than well good enough. It doesn't have to be cryptographically secure. So, but I use a cryptographically secure one anyway. Why not? Because it doesn't cost me more code and more CPU. So very good ones. I use RC4. That's not even a perfect one, but it's more than strong enough and more than good enough. Someone else? No? Looks like someone was raising their hand. Okay, so that's a little about throttling stuff. And we'll look at that more. This picture isn't really, this graph isn't very good, so don't try to interpret it because I realize people misunderstand it. But throttle balance slotted broadcasts. That's kind of one of the important types of broadcasting I do. The title is I wasn't space enough to get into the slotted part. What I discovered after a while was when we broadcast stuff over the network, we don't need to reach all nodes, because if there are 1 million nodes and I broadcast 1 million nodes, don't need to know about me, my node. It's enough that I reach enough many nodes, or rather that each node gets enough incoming data. So usually I can design the algorithm in that way that I collect enough data and the guys broadcasting, that's not that, that's tell them well they exist, but they don't gain from that themselves, or at least the receiver that gains usually. So we can limit how far we broadcast in different ways. Have to look at the figures.
And is that done like on a half or time to days or?
Yeah, I'm actually getting to that in a second. Yeah, okay. This throttle slotted balance broadcasting is actually all three of that. It's ground-based, it's throttling, and it's randomized. So it's actually used all the things to prevent flooding. First of all, we use a time-to-live counter, but it's actually not a time-to-live counter, because all systems in the world, as far as I know, they use a time-to-live counter that counts from, say, 30 and down. And when it reaches 0, you throw away that package. The internet used to use 30, and somewhere 10 or 15 years ago, that wasn't enough, so now they raised it to 60 hops. So our software that only can jump 60 hops can't reach parts of the world now. Or old operating systems, the IP stacks. And that kind of shows the problem if you count downwards. So I realized you have to count upwards. That's much smarter. If You start at 0 and count upwards. When it gets so high, nodes throw it away. And then you can actually balance it. So a node that gets, for instance, you should get one message a minute from each of your neighbor and send one message further on to your neighbors. So you're going to get 5 messages and pick one to send to your neighbors. Then it doesn't matter how high the hop catcher is. You just take the lowest one, the youngest message, and forward that. So it doesn't matter if the hop catcher sends 1005, but that's the youngest one, you broadcast that one to the neighbor. So we don't limit it upwards, we just take the youngest one. So then it doesn't matter how big the network is. You can get connected galaxies, so we don't bother about the size of the hops. So always count upwards.
But doesn't that mean that it's continually talking even when it doesn't need to?
Well, for most of the system we have to idle mode. They have to be idling. If the users aren't doing anything, you still have to keep the network together, keep it consistent, and have a
Continually talking, but those need to.
The network still have to be there.
Yeah.
So you have to maintain it because the node might come on and offline even though people
Is that not the sort of the older definition of gossip?
no,
Okay.
not the one I'm thinking of.
Okay.
So you're not younger is nearer, so that locality, right?
Yeah, when you broadcast, yes. So for instance,
Locality practice, across the
yeah.
network. And that's maintained as a network change structure.
Sorry?
No, it's maintained as a network change structure all the time. You optimize
The nearest one, yeah.
the
So, for instance, if I have to look at my papers. Yeah. So, for instance, if some node is broadcasting that I have this service, if there's only one node in the entire network, and we have a million nodes, of course that message will reach everyone because that will be the youngest message. That's the only message. But if everyone has that message, you will only reach some of your neighbors and further away. But that means each node will at least know about some people supplying that service, so that's good enough. So that's throttling. Yeah. Also, that also balances it. That means that each node will be at equally visible. So every node that supplies this service will, for instance, if there are 1,000 nodes in the network that does this service, 1,000. Just a limited number of nodes will see each of them at about the equal amount of nodes. That means when people are then connected and consuming this server, they will each get as many consumers. So let's see if it's 5 links and 1 message. If we just forward one of the youngest message, then I think if it's 1 million nodes and 1,000 people supplying service, then each one will be 5,000 nodes, I think. And that's actually equally visible, and that's balanced for me, that's the word. And then we need to slot it sometimes. That's, for instance, if we have different services with different names, then they can't just broadcast on the same kind of broadcasting, because if there's 1 million nodes providing one service and one node providing another kind of service, it will just drown out. It will just be visible among the closest ones, and people won't know about that one. So we have to, for each name or each what thing you're broadcasting, or type of broadcasting, you have to have its own slot and broadcast balance that separately. So you have to handle that as another kind of broadcasting. And that I call slotted, but I don't know. So what I just showing here, trying to show is that someone is broadcasting and reaches half the network, and the other one is broadcasting the same thing, and we reach half of the node. So this one knows about both, but this one just knows about one.
So they know if they've received the same message the second time. So the pink and green nodes know that they've received the same message.
Because it gets from one direction, get one data, and from another data.
Yeah.
But usually we don't broadcast one, because knowing just about if you file links just 5 can be a bit low. So usually we, for instance, forward 5 node addresses of each link. So let's say 4. So each node will in total know about 20 nodes, so that's in many cases enough. But it depends on what we need to know about. This is just a little about broadcasting. So I'll show how to use it later on. So, yeah. Oh, okay. This is just one kind of broadcasting. We'll use many kinds of broadcasting later. Okay, a little about what we can do. And these ones are actually broadcasting based, all of them. We can count the number of nodes online in an efficient manner with the cost It cost me just a handful of